Hello everyone, and welcome to Lab Manager's Product Spotlight webinar series. These webinars are designed to help attendees understand a specific proprietary service or technology and where and how it can be applied in an effort to help labs operate more efficiently. My name is Trevor Henderson, Technology Editor for Lab Manager, and I'll be moderating today's webinar entitled Measuring Size, Stability, and Conformation of Biopolymers with Dynamic Light Scattering. We like our webinars to be very interactive, so we encourage you to send us your questions at any point during the presentation. Many of you know the drill, but for those of you just joining us, you can ask questions simply by typing your query into the question box, which is located at the bottom left-hand side of your screen. We'll try to address as many questions as possible during our Q&A period, and if we happen to run out of time, I will forward any unanswered questions to the presenter, and he can respond to you via email. Additional resources can be accessed through the resource window or through the documents icon located at the bottom of your screen. You may also move or resize any of the windows simply by grabbing them at the top or stretching them at the bottom right corner. At this time, you may need to move or minimize some of the open windows to see the live view. This webinar recording will be available early next week on Lab Manager's website, and at the end of this webinar, we'll share that link with you, as well as the contact information for today's speaker. At this time, I'd like to introduce our speaker who joins us from Wyatt Technology. John Sampayne is the Senior Application Scientist and Northeast Regional Manager for Wyatt Technology. John graduated from the Biochemistry and Molecular Biology Department at the University of New Hampshire, and since joining Wyatt has provided a range of analytical support and expertise in the use of multi-angle static and dynamic light scattering, field flow fractionation, analytical ultracentrifugation, circular dichromism spectroscopy, UV-vis spectroscopy, fluorescence spectroscopy, and calorimetry. John, thank you for joining us today.
Thank you, Trevor, for the introduction. And thank you for joining us for the webinar this morning. Basically, what we wanted to talk about today is about our dynamic light scattering line of instrumentation. And just to give you a bit of background, Wyatt Technology, we've been making instruments since about 1981, static light scattering instruments. And we worked for several years with a company called Protein Solutions for incorporating their DLS line of instruments, traditionally batch systems, into our online static light scattering system. And in 2004, we had the opportunity to purchase Protein Solutions, not only for their world-class line of industry-leading DLS batch instrumentation, but also for the crown jewel, which was for their plate reader technology. So it measures dynamic light scattering directly in the plate. So this webinar is really designed to go over some of the applications that we have been working on over the years, both at Wyatt and on this technology. And to start with, I think the most important is what can light scattering measure? So traditionally, our light scattering systems have been static light scattering systems. So they've been for measuring molar mass, a weighted average molar mass. We can also measure the root mean squared radius, and because we measure mass first principle, we can measure the second virial coefficient, or the non-ideality of scattering. Dynamic light scattering is taking the same really principles, but it's measuring the scattering intensity over longer periods of time. So what we do is we take the data and we look at the diffusion coefficient, and we can derive the hydrodynamic radius through the Stokes-Einstein equation. For phase analysis light scattering or measuring electrophoretic mobility, we still use light scattering for that application, but we look at molecules moving in a charged environment, so we induce an electric field and look at their movement based on the charged state of the molecule. For this, it's out of the range of what we're going to talk about with today's webinar, but if you'd like more information, you can visit our website at wyatt.com and find out more information about the pulse. So just to start about how Rayleigh light scattering works, and this is fundamental for both static light scattering and dynamic light scattering because we talk about both during this presentation. So Rayleigh scattering in a static light scattering sense, if you know the concentration and you know the mass, if you know the concentration and you determine the scattering intensity, you can derive the mass. So it's a first principle measure of mass. variations in scattering intensity with respect to the angle of which you're observing the scattering. So you can see if particles are relatively small, they scatter what's known as isotropic in nature, and relatively small based on the wavelength of light that we're using. If molecules are larger, they'll scatter more in the forward direction. Again, molecules are larger based on the wavelength of light that we're using, and that's known as anisotropic scattering. And this is important with dynamic light scattering because if you have a mixture of both small and large, this will dictate the best angle at which you can collect intensity for both of those mixtures. So what can batch DLS measure? So batch DLS, remember, we're measuring the hydrodynamic radius of molecules based strictly on the translational diffusion coefficient. The size range of this runs in the smaller end of about 0.5 nanometers. And because we're Rayleigh scattering limited, or based on the principles of Rayleigh scattering, a micron is really the upper limit for Rayleigh scattering. That being said, the Nanostar can go up to as high as 2.5 microns in size, and in reality, dynamic light scattering can measure particles that are much, much larger. But according to Rayleigh scattering, we are at that upper limit of about a micron. We can see changes in the average radius down to about 1% change. So what does this mean for most molecules? Well, specifically for proteins, we can see a change of about a 3% dimer by weight. So we can really start to see if the molecule is starting to self-associate. We can accurately quantitate polydispersity, which is to say changes in the peak width of our sample. So we can do that up to about 30%. So if you're looking at a range of different material in solution, we can tell quantitatively what each of them, the amount of each of them in the final results. And we can resolve two species, but they have to have a difference enough in their diffusion coefficient. The rule of thumb is roughly about 4 to 5 times different in the radius, and it's a weight factor of about 60 to 120. So we can't see differences necessarily, distinct differences in monomer and dimer. We can certainly see if there's dimer present, but we'll be able to start seeing apex resolution if we go about 4 to 5 times different in the radius. We can also quantitate distributions, and we quantitate them based on the percent mass for species up to 200 nanometers. So what this will allow is we can actually figure out if there's a number of species present. We can quantitatively determine the values of each of those. And we can detect presence of species much larger, as I said, to hundreds of microns, thousands of microns in size. But as far as quantitative, we have to stay below that 200 nanometer to get an accurate quantitative value. For dynamic light scattering in theory, what we do is we use an avalanche photodiode as opposed to static light scattering, which specifically uses a silicon pin photodiode. And an avalanche photodiode, what it will do is it will give us sensitivity over a broader range, which is to say over a broader range of time. So if we look at molecules moving with respect to one another, the data essentially looks as a function of light intensity fluctuations over time. And it would make sense that those fluctuations, the spacing in those fluctuations, will dictate the molecule's diffusion or Brownian motion. So what we do is to look at those spacing fluctuations, we use an autocorrelation analysis, and the results actually are reported as this decay rate. So it looks like a sigmoidal decay rate, and from there we can derive the diffusion coefficient, and if we manipulate this decay rate mathematically, we can also derive a distribution or a hydrodynamic radius. And this is a histogram, is traditionally what it's referred to. And you can see this bar graph. And that's to differentiate dynamic light scattering data from traditional chromatography, because very often you'll look at DLS data and it will look like chromatography. So traditionally it's transferred to this histogram or bar graph looking results, just to, again, differentiate DL. So analysis for size information. Here you can see with BSA, or bovine serum albumin, we've analyzed this in a pure sense, and you can see the nice correlation curve as a result, and it gives us a radius of about 3.6 nanometers. And through the cumulants analysis, which has traditionally been used, you can fit it for a single exponential decay. Cumulants only fits a single exponential decay. So if you have a single species in solution, it works out well. In another case, we have polystyrene latex spheres. Again, they're a pure sample, and we've analyzed them through the cumulant analysis. The results look very nice, and they agree with the manufacturer's specifications, in this case 50 nanometers in size. But the challenge has always been with cumulant analysis, what if I have a mixture of BSA and polystyrene? The results, in fact, would look like a combination of those two correlation curves. Well, with cumulant, since I can only fit a single exponential decay, the results would be weighted more towards that polystyrene latex value. So we've converted the analysis, and we use what's now known as regularization analysis. And what it can do is it can actually fit each of those independent components, and it can give us information about both of them, even though it's a mixture. So we don't have a single species of each. Both of them have been mixed in the same concentration. And the results will actually, you can see each of the individual species. Again, the rule of thumb is about 4 to 5 times different in the radius, and in this case, it certainly is being fulfilled by the span between BSA and poly. So for the results, what you would see for regularization analysis, in this case, this is BSA here just for reference as a single species, and polystyrene latex, again, for reference just as a single species. And then when you mix both of them in, and keep in mind the concentrations of both are equal, the results will look like this. So here you can see each of the individual green species, and they relate to the BSA and the polystyrene latex. And you can see the effects of the mixtures between the two. Because polystyrene is so much larger, and the scattering intensity is based on a weighted value, you'll see a proportionally greater scattering intensity on the polystyrene latex versus that of the BSA. So you always have to worry about mixtures between very, very small things and very large things to make sure that you have adequate scattering intensity to represent. Here we can see estimating the distribution of not only seeing the individual species, but we can also calculate the individual polydispersities for each. And even though this is a low resolution method, as I keep saying, about 4 to 5 times different in the radius, you can resolve species even if they fall below that, and you can see changes in the overall shape. So you can differentiate, even in the case of a monomer dimer, even though you may not be able to resolve the dimer, you can start to see the effects of the dimerization on the peak shape. So how do we measure? As I mentioned to you, we purchased Protein Solutions for the patent on measuring directly in the plate. And here you can see we measure backscattering up off the bottom of the plate at about 170 degrees. And our laser actually goes right up through the plate. So as long as the meniscus position in the plate does not interfere with the reed position, which is about 1.5 millimeters up off the bottom of the well, we can make measurements. So in this case, we have a very good handle if there's a mixture between small and large, because we're measuring at backscattering. And the larger species, the intensity tends to drop off with respect to the angular position, whereas the smaller species has the same intensity regardless of the angular position. So this is good in the case of mixtures. It's also good in the case if you have a large species that will come down in the volume. It will tend to drop down towards the bottom of the well. And in this case, it has no place to hide, because in the plate reader, we measure up off the bottom. Here you can see an actual image of what the well. So the plate reader 2, again, we measure directly in microwell plates. The same instrument can measure a range of different plate formats from 96 to 84 to 1536. It would be based strictly on the volumes that you use, or traditionally, if you've been comfortable in your lab with using one format, you can continue to use that format. It just has to be a flat bottom plate, and it has to be a clear bottom plate. We can make measurements in the well in just a few seconds, and it takes a fraction of a second to move to the next well. As far as concentrations or sensitivity, because sensitivity of light scattering is always based on mass and concentration, we have to quote both of those. So here for lysozyme at about 14 kilodaltons, we can get away with 0.125 mg per mil. And this is, as far as the mass, is roughly linear for the association, for the sensitivity. So if we increase this an order of magnitude for something like an antibody at 150 kilodaltons, we can change that concentration value, move that decimal point 0.01 mg per mil. So it's a very sensitive instrument. Temperature range from 4 degrees to 85 degrees. We have an automatic adjustment of the laser and the attenuator. So basically you can just fill this well, fill all of the plates, hit go, and the measurements will all be made automatically. So, and that will allow us to screen a wide range of samples and conditions. And we can also interface this with robot liquid handling systems. We really wanted to have more of a high throughput nature. Here you can see this is an implementation of DLS in the high throughput environment. This photo is courtesy of FreeSlate, but in fact, we can incorporate this technology with any of the robotic systems out there, from the Hamilton to the TCAN. So whichever you're familiar with, we can incorporate our systems. And the robotic sample prep can take place, and then we can coordinate it with our software to open up the door automatically, and then all of the data can be transferred, if you chose, to a database for further analysis. So some of the plate reader advantages: again, samples are measured directly in standard micro-well plates, so you don't have to worry about any contamination. Measurements can be completely automated. We can measure samples in triplicates, so you can have much greater precision, much more confidence in your final value. So it's truly a non-invasive technique, or a non-perturbing technique. No cross-contamination due to using cuvettes or potentially transferring, and certainly no precious time wasted for sample transfer or cleaning of an optics. And these plates are disposable, so whether you use disposable plates and toss them, or you can use quartz plates. In fact, we found that glass-bottom disposable plates will give similar resolution as the quartz plates. So it's a very cost-effective way of making measurements. So some application examples. In the past, DLS was really seen as being an estimate as to whether your molecule was self-associating. And we realized very quickly that the technology had much greater potential. Not only did we work on applications in-house, but several of our customers got in touch with us and had some very interesting applications as of the past several years, so we'll talk about those. And applications include measuring aggregations and formulation development. Pretty standard, that's been a typical application for us. Temperature stability for looking at protein melting. Small molecule aggregation, associations, even turbidity and viscosity measurements. And then at the end, we'll talk about changes in. So this example was sent to us based on changes in the monoclonal antibody, both a pre-lyophilized and a post-lyophilized. And here you can see that you have the main species that shows up, and the height of the species indicates, of course, the concentration. And with the post-lyophilization, whether there's sucrose present or not, you can see the main peak actually drop down, so indicating you're losing some of the main species to some higher order associated material, and you can see that showing up there. So a significant amount of aggregates that's showing up on at or about 100 nanometers in size. So traditional DLS formulation optimization. So you can assess degree of aggregation as a function of a number of different variables. Traditionally, this is a platform approach that's now been adopted, so changes in pH, samples, salt, excipients, or various stressors are all known. You just simply generate a plate based on this platform approach. Your samples will be introduced into that plate with a variety of different conditions. And here you can see this was forced aging for about 40 degrees for 2 weeks. And the heat map, or the color indications, show, for the darker colors, show self-association or aggregation that's present. And the lighter colors show where the molecules are more stable. So what you can do is you can run this and then look at this heat map at the end, and then pull out those lighter colors which indicate that the molecule is stable. And from there you can go on to do further studies or through different orthogonal techniques. But what this will do is really narrow down the range of conditions that you have to further test for relation groups. And because it's automated, it can significantly lower the barrier to test all of these conditions, as well as any issues that arise from sample handling or error from the end user. It can be also used for determining stable conditions for formulations, and this is a relatively well-established application for DLS. Here you can see these crystals actually forming directly in the wells as a result after a screening technique with. For liposomes, liposomes another very popular application. Traditionally, you've used fluorescence for this, but you've never been able to really see what the liposome formation looked like until scanning with DLS. And here's an example of two techniques for generating liposomes, both the sonication and microextrusion technique. The microextrusion technique will generate generally a more homogeneous or monodisperse liposome, and you can see that by the two sharper peaks in green and yellow. And then the sonication techniques generally will not be that good at generating a discrete peak. And here you can see some smaller material that's formed as well as some higher order material. And then when those liposomes actually are filled with a drug component, you can see that there is a subtle change in not only the peak height, but the peak shape and the apex has shifted a little bit to the left, so it shows a smaller size, and as well as some higher order material that's been formed, and you can see those two peaks that form over to the right of the main peak. And these results have also been confirmed independently through field flow fractionation coupled to multi-angle static lights. But this is a very nice screening tool to show the comparison between filled and unfilled. As far as temperature dependence, this has been a pretty wide application for us as well. Again, we're not going to replace calorimetry, but because that is such a time-intensive and sample-intensive technique, we can do this as a screening tool with the plate reader. In this case, we've looked at ribonuclease A, the melting temperature. So we've scanned this over a range of temperatures from about 15 degrees all the way up to about 75 degrees. And the shift in the radius to start with is likely due to the viscosity. You can see the data here has not been corrected for the viscosity. But if we look at this ribonuclease A as a function of concentration and temperature, we can measure the midpoint, and we can manipulate the conditions, whether we add excipients, whether we add different salts, and we can see if that midpoint changes. And effectively, that will show changes in the overall stability of our molecule. This group has chosen to manipulate the data in such a way to represent ribonuclease A as a function of calcium chloride concentration. And as you can see, that midpoint of transition drops, showing a less stable ribonuclease A as a function of an increase in the calcium chloride concentration. So just an interesting study that they did, again, based on this one. If you want to look at, in this case, RNA unfolding. So this group looked at RNA at elevated temperatures. It was 37 degrees over a period of time. And you can see the shift from the native RNA, and the hydrodynamic measurement is 3.8 nanometers, to an intermediate state at about 4.3. And then the final state that was measured, or the unfolded condition, at 5.7 at the end of the study. This group actually went one step further, where they looked at the comparison between the DLS measuring hydrodynamic radius versus small angle X-ray, which measures the root mean squared radius. And the root mean squared radius is the same measurement that's done through multi-angle static light scattering. And that's the sensitivity of the root mean squared radius, or here as an R sub G as it's depicted, is looking at changes in the actual mass distribution, whereas DLS looks at the hydrodynamic changes of the molecule. So they have different sensitivities. And if you look at a ratio of the two, and in this case between native, intermediate, and unfolded, the ratio will change, and that ratio reflects the unfolded nature of this molecule. So from 0.9, a ratio between the R sub G and R sub H shows the native structure all the way up to the unfolded at about 1.2, all the way in some cases up to 1.5. So this has been used for quite a few years, and you can either make this comparison with DLS and small angle X-ray, or more commonly made the comparison between DLS and the R sub G measured by multi-angle stat. Here's an example of protein heteroassociations. So in this example, and we'll go back to the first slide that I showed, and the first slide was talking about the scattering intensity. So the scattering intensity is based on two variables. It's based on mass and concentration. Now, as I increase concentration, I generally see a linear increase in scattering intensity. But as I increase mass, I'll see an exponential increase in scattering intensity. So in this case, we looked at an established system. It's soybean trypsin inhibitor, and that's in red, and it binds chymotrypsin, and that's in blue. And we can see that if we change the ratio of the two relative to one another, we can see a change in the apex, or the signal intensity. That line in blue is where I see no binding. Now, if I saw a stoichiometry of 2 to 1, meaning 2 soybean trypsin inhibitor to 1 chymotrypsin, what I would see is I would see an apex that would shift more to the left. If I saw a 1 to 1 binding of the two, I would have an apex value that would be closer to the center. Or if I saw, in this case, a 1 to 2 stoichiometry, you can see the apex shifts to the right. And again, the blue line is representing no binding, so there's a small molecule, an AEBSF, so that inhibitor actually binds to chymotrypsin and it blocks binding to the soybean trypsin inhibitor. So that's our control state. In this case, we just looked at a ratio of these two binding components at various temperatures from 5 degrees to 37. We did 22 concentrations, 5 replicates per concentration. And not only did we get stoichiometry to agree with established and published results, but we got a KD value that, based on fitting the curve, that also agrees very well with published results. And this information, or this study, was published in Biophysical Journal in 2010. So compound aggregates, this promiscuous inhibitor application is actually one of our more popular applications. In fact, we teach a component of this in our Dynamic Light Scattering University course, where small molecule drugs may form aggregates that inhibit enzymes, and they do it in a non-specific way. So the goal of this application is really to identify those false positives. And they act either non-specifically or non-competitively, and they have very poor selectivity. So the function of this is looking at a range of concentrations for this small molecule, and the compound in this case is in 1.5% DMSO. So the concentration series in a range of buffers will reveal the aggregation concentration, which is to say this small molecule really can't be seen by DLS if it's just in a single state. But as it forms an aggregate, you can now see that sigmoidal, or that curve, so you can see that aggregated state. And we don't see the small molecule in a single non-aggregated state until we drop below that 9 micromolar. So it's a very nice screening tool to be able to eliminate those false positives. Here's another interesting application where one of our customers thought they were looking at the Stokes-Einstein equation, and they realized one of the components in the Stokes-Einstein equation is, of course, viscosity. So in this case, they wanted to exploit that characteristic, and you can see that we see our viscosity as a function of protein concentration in various curves. And you can see, of course, they've overlaid the viscometer in squares versus the DLS results in circles. And the way they were able to do that is, if you can see in the inlaid graph, you can see the main species on the left, and then there's a darker blue species or darker violet species on the right. And what that is a bead, and it's a bead of a known size. It's a standard. And as long as the bead does not interact with your main species of interest, you can spike that bead into solution, and it stays at a very low concentration. And simply in the software, you just input in the radius of the bead, and the only other variable that will be left is solution viscosity. So this is a very nice technique for a screening tool. In this case, this group was looking to try to look at a series of different excipients or salt concentrations, salt components, to lower the viscosity of this particular therapeutic. And they looked at a range of concentration from very low all the way up to about 140 mg per mil. And you can see, as a screening tool, it's very effective, and it compares very nicely to a proper viscometer, in that, in this case, 50 millimolar calcium salt was added, and you can see it dramatically lowering that overall solution viscosity. So again, it's not going to replace a standard viscometer, but those take several mils of material, and as you can imagine, over the concentration range, it ends up being quite a bit of material that's used for this technique. For a screening tool, an initial screening tool, DLS does a very, very nice job, and it can do so with very low amounts of material. So measuring interactions with DLS, traditionally interactions, measuring thermodynamic interactions, have been based on techniques that can measure mass first principle. So traditionally they've been analytical ultrasonification, and specifically sedimentation equilibrium, or multi-angle static light scattering. Well, back in the mid-'80s, there was a group that did a lot of work with analytical ultrasonification, run by Steve Harding, that looked at this application and was traditionally using changes in sedimentation as a measure of association. Well, he realized that you could use dynamic light scattering to also look at potential associations. So where you see dynamic light scattering, again, you measure the diffusion coefficient. So changes in that diffusion coefficient could indicate the propensity of a molecule to self-associate. So the math supports that quite nicely. And in fact, the trends between the diffusion interaction parameter, it's known as KD. It's not the same dissociation constant that we're used to as far as association from the previous slide. This is a small k, large sub d. So again, it's known as the diffusion interaction parameter, and it's related to the parameter, the thermodynamic parameter that we traditionally would use with either multi-angle static light scattering or sedimentation equilibrium, such that if we see association, we'll have a negative KD or a negative A2, and if we see dissociation based on thermodynamic differences between solvent and solute, we'll have a positive KD or a positive A2. So again, if you want to see this as a tool to screen associations, measuring the KD is a very fast and effective tool. It doesn't take the 20 to 30 minutes that it could potentially take to generate a Zim plot and measure A2 with static light scattering, or the 5 or 6 days it would take with sedimentation equilibrium to measure a similar thermodynamic parameter. And the question is always, does it relate to the A2? Well, this group, Larimeyer et al. At Roche, did this measurement where they looked at the KD values that were measured for the system as a function of the A2 values that were then measured. And you can see they fall very nicely on this linear line. So if you're looking at just trending of these association characteristics, you can use KD as a very nice alternative to the A2 parameter. And this is all done in our software now. It's all automated. So turbidity is another important factor, especially related to a lot of the biological therapeutics that are out there. Once you get to those higher and higher concentrations, the customer or the patient actually seeing the sample being a cloudy therapeutic is not that reassuring. So the FDA wants to make sure that the turbidity value is held to a very low value, and that can also indicate some potential immunogenicity if you have a very highly turbid sample. So turbidity has been a relative challenge to make. In the past, what we've done is we've used some European pharmacopoeia standards where we've generated these standards, and they've given us a series of vials, in this case from very low turbidity to high turbidity. And what you would do is subjectively compare your sample to these EP standards, and you would relate the turbidity based on that comparison. Well, with light scattering, we thought we could do one step better than that. So we used our plate reader to actually give us the turbidity units that we can transfer over based on changes in overall intensity of scattering. And you can see here that there's a very nice linear value of change in the overall intensity to the NTU units. So you can use light scattering, in this case dynamic light scattering, of course, as a function of turbidity. And not only can you do that, our instrument also has a camera on board. So if you wanted to see changes in turbidity and relate those to a potential self-association, or as you can see in these examples here, you can see bubbles present, you can see some oil droplets, as well as crystal formation. That camera is taking an image every single time you make a DLS measurement. So you don't have to go back and try to figure out why your samples looked odd in the final results. You can actually now get an image that's taken automatically when the measurement is made, so you can actually see if there is something in the well itself. So making a shift slightly into the other line of DLS batch systems that we acquired from Protein Solutions. In this case, we call this our DynaPro Nanostar. And the Nanostar allows us, it's based on the platform of our static light scattering system, so it's a very precise optic bench. We've left in a silicon pin photodiode to measure static light scattering independently. And as you can see on the right-hand side, we also left in an avalanche photodiode, or incorporated an avalanche photodiode to measure dynamic light scattering. Now, there has always been a question when you make a dynamic light scattering measurement and you see a change in the radius. Does the change in the radius indicate an unfolding component of the molecule or potentially a self-association of the molecule forming a higher oligomer state? And this question has been tried to be answered through a range of different techniques. I've even heard of an instrument that incorporates a Raman scattering component into DLS to answer this question. Well, the Nanostar has been doing this very successfully for over a decade now, where we've been able to independently measure the static light scattering and independently measure dynamic light scattering. So now we can tell you if it's a change in the hydrodynamic characteristics is also representing a change in the mass of the. So in this case, we looked at lysozyme as a function of temperature. And you can see the change of lysozyme. Here we can see the radius change as a function of temperature. And you can see that nice characteristic curve or unfolded nature of the molecule, or is it unfolded? So the question is, as we see that change in that hydrodynamic characteristics as a function of temperature, is that unfolding or is it oligomerization? Well, here this display shows that same radius in green as a change in temperature. And then on the right-hand side, we can see the mass measured independently by static light scattering, and that's in the teal downward-facing triangles. So the mass doesn't change at all as a function of this temperature, indicating that lysozyme, in fact, is not forming a higher-order oligomer. It's just merely unfolding in the state. And what we found is that with lysozyme, we could actually even cool it down, and it would go back and refold because it didn't form that higher-order oligomer. So this is a case where we can clearly see, and very quickly, and this is a 1 mg per mil lysozyme in a pH4 acetate buffer as a function of temperature, we can very quickly see and easily see that this is in fact merely unfolding and not. As far as comparison, we often get the question is, how does dynamic light scattering compare to other techniques out there that look at association states? So in this case, we looked at X-ray diffraction, transmission electron microscopy, and QELS. So the X-ray diffraction technique will give us a mass average, and the average of that technique is about 50 nanometers. Keep in mind, these are all batch techniques, so we don't do any sort of separation ahead of time. If you look at the X-ray diffraction value as a function comparison to transmission electron microscopy, because TEM gives you a relatively small non-native sample size, you can look at the values here. They've been artificially skewed in the lower range, closer to 33 nanometers. So really not a true depiction or true comparison to X-ray diffraction. Whereas if you look at DLS, you can change the sample size that you want to look at. You can change the sample time that you want to scan. You can change, of course, the sample conditions. And it's a non-invasive technique, so it's a true batch free solution technique. And here you can see the comparison with X-ray diffraction is very nice. And not only is this a non-invasive free solution technique, but it's a very fast technique. Keep in mind these measurements can be made in a few seconds to a few minutes, depending again on the range of time that you want to. So in conclusion, dynamic light scattering will very accurately measure the hydrodynamic radius and precisely to determine things like proteins associations, liposomes, particle size distribution, and aggregation, both in a non-mass action sense, so where you form monomers and dimers, but also in a non-mass action sense, where you form monomers and then higher order oligomers. We can very nicely look at temperature stability studies, and keep in mind that's of polymers and proteins. So we can measure in aqueous or organic solvents. So if you wanted to look at temperature stability, that's something you can do quite easily. Association equilibrium. I showed you in the case where we looked at the soybean trypsin inhibitor binds to the chymotrypsin. So we can look at association equilibrium and actually even give you a value of that equilibrium state. And you can do that with either the plate reader or our cuvette-based Nanostar. Batch dynamic light scattering is a very easy-to-use technique without any chromatography development. And in fact, it has a very high throughput capacity, which requires very low samples. With the Nanostar, we have a quartz cuvette that we offer. That's a 1.25 microliter quartz cuvette. We also have a disposable cuvette for the Nanostar. It's a Wyatt manufactured cyclic olefin polymer cuvette, which takes as little as 4 microliters of material. As far as the plate reader, on the low end, as far as volumes, the 1536 well plate is about 3 microliters. The 384 half volume is about 20 microliters, and the 96 well plate realize is approaching between 75 to 100 microliters. So it depends on either the format you're traditionally used to or the volume requirement for your measurement. So batch DLS in combination with static light scattering, as in the case of the Nanostar, it's able to distinguish between unfolding and oligomerization or aggregation of the species. So with the Nanostar, you have that single angle static light scattering silicon pin photodiode as well as the avalanche photodiode that are making those measurements both at the same time. The other thing I just wanted to quickly bring up is very often what we'll do around the country is we'll put on regional users meeting. We've had our meeting in Boston as well as our Mid-Atlantic meeting, but we have a meeting that's upcoming on May 12th in the San Francisco Bay Area, and then another on June 7th in San Diego in Southern California region. So it's a really nice interactive opportunity. So you can meet other users. They have presentations on their work, specifically, of course, with Wyatt light scattering systems. And then we have several presentations as Wyatt staff members that we give based on some of these unique applications that I've just mentioned with both dynamic and static light scattering. And then we also talk about some of the latest innovations that we're offering, both in terms of our hardware and software. The topics include biophysical characterization, formulation, stability work, measuring aggregation, again, mass action, meaning the smaller to non-mass action where we'd see those larger components being formed. And then, of course, biomolecular interactions with both size exclusion or any chromatography coupled to moles, or field flow fractionation coupled to moles, or our Calypso CG coupled to moles. And again, we talk about dynamic light scattering, static light scattering, and even our MP pulse to measure the electrophoretic. And if you're interested in finding out any more information, you can visit us at Wyatt.com, where we have a series of application notes that are listed. We have also a searchable bibliography. So if you're interested to figure out what type of applications would be applicable to your specific molecule, you can just type that in and it will come up with all the papers that we have. At last count, I believe we had over 13,000 peer-reviewed papers. So it's really interesting to see who's using the instrumentation, how they're using it. And the final thing is that you can search specific by the instrumentation. So if you just want to see applications based on DLS, you can search for that. Static light scattering, even field flow fractionation, search specific. And of course, as always, if you had any questions and you're a current user, you can contact us directly at info@wyatt.com, or support at Wyatt support. And with that, I just want to thank you for joining us, and I believe we have plenty of time now to take any questions that.
Excellent. Well, thank you, John. And we will move directly into our question and answer session. There is a number of questions that we need to cover. And for those of you who may have joined us late, you can ask questions of John simply by typing your query into the question box, which is located at the bottom left-hand side of your screen. So, John, can DLS provide molecular weight information, and how would you go about calculating it?
So this is a great question. In fact, this is a question that comes up very often. So dynamic light scattering in and of itself measures through the use of an avalanche photodiode, measures the translational diffusion coefficient. So that's really what DLS does. From there, you can manipulate that diffusion coefficient through the use of the Stokes-Einstein equation to pull out hydrodynamic radius. And then from there, if you look at a series of standards, you can derive a mass based on the association of a conformation of a standard versus the hydrodynamic characteristics of your molecule. But it is second principle. And it's the same type of association that you would get from size exclusion chromatography, where you run standards, and based on their hydrodynamic characteristic, they come off at a certain elution position. And then you would look at your elution position from your molecule, and you would say, based on that elution position, it's got to be this mass. So it's not first principle with using strictly dynamic light scattering. And that's why with the Nanostar, we incorporate that silicon pin photodiode to give us first principle information about the mass. So you can independently measure the mass as well as measuring the hydrodynamic characteristics with DLS. So DLS in and of itself, even though it reports a mass, it's based on a comparison to standards, so it's not a direct measurement.
Excellent, thank you. Now, you mentioned that you could measure viscosity by DLS. Could you elaborate on that a little bit?
You bet, you bet. So if you look at the Stokes-Einstein equation, many of the parameters are already known. One of the parameters that's generally a variable, especially if you look at changes in temperature or changes in concentration, would be the solution viscosity. And if you don't correct for it, you can see an artificial change in the hydrodynamic characteristic as a result. So in this application, we did not know what the solution viscosity was as we changed temperature or as we changed concentration. But what we could do is we could spike in a bead that we knew the size of that bead very well. And then in the software, as long as the bead doesn't associate with our main species of interest, which of course we'll be able to know because we're measuring it with DLS, we put in the radius of that bead, and the software back calculates using the Stokes-Einstein equation what the solution viscosity is. So even though it's not a direct measure of the solution viscosity, it's a mathematically calculated or derived value of solution viscosity based on the experimental conditions that I just described. So this is something that came about several years ago. It was published in 2011, and there are several groups that are now using this on a regular basis, and it's a fully incorporated component in our software. So it's something that can be done relatively easily.
Excellent, thank you. Now, John, is it possible to have SLS and DLS capability in a single instrument?
Oh, sure. And in fact, our Nanostar really encompasses that component. What you can't do, or you're tempted to do, is use dynamic light scattering as a quasi-static light scattering instrument. And really the trick there is you want to make sure that your scattering intensity is linear as a function of concentration. Well, if you've used an avalanche photodiode in the past, or you understand avalanche photodiodes that are traditionally used in DLS, they're a very sensitive instrument. The rule of thumb, for every 1 photon of light that hits an APD, it will measure that intensity about 80% of the time. The problem is when that APD tries to recover and get another photon, several will have passed. So it's not linear as a function of concentration. Whereas with a silicon pin photodiode that's used for static light scattering, That doesn't have the sensitivity over time that an APD will, but it's very linear as a function of concentration. So if you wanted to measure both static light scattering and dynamic light scattering, it's essential to use an instrument that has both of those capabilities, and that's the Nanostar. So our Nanostar was built on the optic bench of our three-angle Treos static light scattering system, where we have left in the 90-degree silicon pin photodiode for static, and we have the 90-degree angle, the other 90-degree angle for measuring dynamic light scattering through a separate avalanche photodiode. So that would be our Nanostar.
Excellent, thank you. Now, how much sample is required for Dynapro plate reader measurements?
Right, so it's a good question, and the volume is really based on the plate format that you choose. So on the low end would be the 1536 well plate, and that has anywhere from about a 3 to 4 microliter for the low volume for that system. Then if you switch up to a little bit easier plate to load and a larger format, which would be the 384 well plate, you could choose a traditional 384 well plate with a square well, and the volumes on that are about 40 microliters. You can also choose a half volume 384 well, and instead of being a square well, it would be a circular well. And the volumes in those cases are about 20 to 25 microliters. And then the largest format that we can utilize with our plate reader is the 96 well plate, and that can come in a full volume, which I mentioned is anywhere from 75 to 100 microliters. You can also get away with a half volume 96 well plate, and that's about 50 microliters. So depending on the format of plates that you may already have in-house and are familiar with using with other high throughput instruments, you can utilize those, or if your sample requirements are such that you need to go to lower volumes, you can easily shift to a 384 or even the 1536 well plate. And keep in mind, there's nothing that needs to be changed in the instrument other than just a quick click on a software component just to select, using a pull-down menu to select the plate format that you're going to choose. And that really just tells the instrument the overall design of the plate so it knows where to stop for the next well.
Excellent, thank you. Now, what is the measurement time per well and the overall measurement time for the plate in the Dynapro system?
Right, so the measurement time per well depends, of course, on the complexity of the system that you're looking to measure. So theoretically, you can make a measurement in as little as a second, and then you can move to the next well in a fraction of a second, make another measurement. So you can scan a 96 well plate very quickly in a little over 100 seconds, in fact. The challenge is that you are going at a great speed, and you don't see a lot of sensitivity. So you're really losing a lot of the subtle characteristics of making a measurement over longer periods of time. So in that case, we generally will say the time to make a measurement is based on the complexity. If you know that you're looking at self-association, you may want to, instead of taking a 1-second measurement, you may want to look at a 5 to a 10-second measurement. Also, you need to consider the size of the material. Larger things, of course, diffuse much slower than smaller components. So you would need to allow for enough time for diffusion to be adequately measured. So making a measurement of a large sample like a liposome that I mentioned, for instance, would not be adequate in a 1-second measurement. So you would need to do maybe 10 seconds or 20 seconds. And then the number of repeat measurements that you made per well would be based on the degree of precision. So if you wanted to have higher precision, you would take that 10 or 20-second measurement and you would do it 5 to 10 times. So you would have much better precision. And then the time that it would take, so you can figure that out, plus, again, about a fraction of a second per well, to move from well to well. And then if you were talking about scanning an entire plate, that depends on the type of scan that you wanted to do. So if you wanted to scan an entire plate, you would take that number, roughly 50 to 100 seconds per well, again, and then a second to go between wells, and then you would multiply that times 384 or 96 or 1536, depending on your format, and that will give you the time it would take to scan a plate. The difference is if you wanted to do a temperature dependence, you would have to ask yourself, do I want to do a measurement in which I set the low temperature and the high temperature and then set a ramp rate and then scan as many wells as fast as I could? Or would I want to go in increments where I go up a certain increment, wait for the plate to stabilize, and then make the same scan of the plate? So that will dictate the time that it will take to not only scan a plate, but also to complete a measurement of a specified value, so a change in temperature or a change in time. So in some cases, the runs may take many, many hours if you're going up for a temperature scan, for instance. But the nice thing is that the system is automated, so you could load a plate, you could set up your program for scanning, you could run it the night before, go home, everything's automated, come in the next day, and you'll have all of your data, and then your instrument can be set at the end of the scan to go into a sleep mode where the laser will turn off and the temperature will be set back to a low temperature setting. So it really depends on the complexity of what it is you're trying to measure and the complexity of your overall experiment.
Excellent, thank you. Now, John, are calibrants required for DLS measurements?
Calibrants are not required. So keep in mind, this is a first principle technique for determining the diffusion coefficient. So the instrument components themselves are all tested to make sure that they operate within the established range. So in that case, you could say that a calibrant is required for the avalanche photodiode when it's first manufactured. But that goes with any component that's used in an instrument these days. But what we do with that component, once we know those values and we know the avalanche photodiode operates optimally within the range that we're asking it to operate, we can simply just use this to measure the diffusion coefficient. And that will give us a series of fluctuations as a function of time. From there, we can calculate through Stokes-Einstein the hydrodynamic radius. But it measures that diffusion coefficient first principle, which is to say it doesn't use any standards to compare to derive that hydrodynamic radius value. So the only time we would use a standard, and those have already been pre-measured and are already in the software, is when we want to convert the resulting hydrodynamic value to a mass value. We do use standards of various conformations, and as long as you put in the conformation and you know the conformation, you use the correct standard approximation, then you can calculate a mass. But again, it's the same mass approximation that you would get from size exclusion chromatography based on an elution position. So initially making the measurement of diffusion and ultimately calculating hydrodynamic radius does not require standards, but then making the further conversion with just dynamic light scattering to mass would require standards. But initially, DLS is a free solution first principle technique for that diffusion coefficient measurement.
Excellent, thank you. Now, clearly, dynamic light scattering can measure a variety of parameters. Now, which DLS analyses would you say are most important for formulation and stability?
Well, so that would, of course, be the most obvious. And formulation and stability, I think, has been one of the longest running application that dynamic light scattering has been employed to do. And for that, it's simply a matter of putting your samples in, as I mentioned to you in that one slide, of using a platform approach where they looked at a range of pH, sample concentrations, salt concentrations, changes in excipients, or various stressors. What they did in that case was just look to see if the monomer or the homogeneous distribution that's initially started off for the sample, if that changes. And you can look at very subtle changes from forming a mass action association, so forming that dimer-trimer association, versus the non-mass action where you form that very high-order material. So DLS as a screening tool, whether it's changes in initial conditions or changes in conditions as a function of time or stress conditions, DLS for formulations has really been used to identify those conditions that drive that higher order material being formed, or those large aggregates being formed. And that's really I think, one of the most important tools or applications that DLS has been employed to do in this regard.
Excellent, thank you. And as I look at the clock, I realize we are running low on time. If we didn't get to your question, please be assured that I will forward them on to John and he can respond to you directly. And this brings us to the end of today's webinar. If you have any further questions or you'd like a copy of the presentation, please consider reaching out to John directly. His contact information, as you can see, is available on the screen. And just a reminder that today's webinar was recorded, and you will receive an email notifying you when the on-demand video is available. On behalf of Lab Manager, I'd like to thank John for joining us today and Wyatt Technology for sponsoring this Product Spotlight webinar. This concludes today's Product Spotlight. I'd like to thank all of our attendees for taking time out of their busy schedules to join us today. And for more information about all of Lab Manager's webinars or to learn more about laboratory tools and technologies, please visit our website at www.labmanager.com. Thank you for joining us and have a great day.